A structural engineer need to deal with a lot of uncertain values, as we will show in this part of the course. How much do you remember from your statistics and probability courses? Maybe a bit, but not too much? Well, this section of the course will provide some elements of repetition of statistics and probability theory, but primarily show how these theories can be used for practical purposes in structural engineering. What is uncertainty? According to Wikipedia, it can be defined as the description of a situation involving insecurity and/or unknown information. It applies to predictions of future events, to physical measurements that are already made, or to the unknown. Uncertainty arises in partially observable and/or stochastic environments. For example, will it rain tomorrow? What will the wind speed be tomorrow? Or what will the maximum snow depth be the next 50 years? Uncertainty also arises due to ignorance, or indolence, which I guess we can also call sloppiness, or a combination of both. Normally, to investigate one such uncertainty in the strength of a structure, I would now have given you all one staple each, and asked you to join in a simple experiment of bending this staple back and forth until it breaks. As this course is online, I can't give you a staple to try, so I made a video of me doing the experiment several times, but if you should happen to have one staple available, please join in. What you do is that you bend the staple open, 180 degree, and then bend it back to its normal configuration, and count the number of times it takes before it breaks. I guess this is the simplest structural capacity experiment that we can do in a classroom. To make some statistics of this, it will take many repetitions, and this will include quite many staples. There you see that the first one broke on 19 cycles. To save a bit of time, I then speeded up the video quite a bit. The process is still to bend them open to 180 degrees, and then bend them back to the normal configuration, and count the number of cycles to the staple break. You could say that this is an experiment of what is called low cycle fatigue, a material degradation mechanism that do occur for some structures exposed to cyclic stresses. Common factors that have been attributed to low cycle fatigue are high stress levels, and a low number of cycles to failure. Historically, low cycle fatigue has for example happened in structures during earthquakes, and during sea transportation of structures on barges. Now you see this is starting to become something similar to a statistical distribution. Here, finally, is the data points after all the staples I could find has failed, describing the uncertainty in the low cycle capacity of a staple. Does this look like a statistical distribution function? Yes, it does. It has some peaks, and the peaks are all that odd numbers, so it seems like the experiment is not fully fair. There obviously is a higher likelihood of me breaking the staple when I'm opening up the staple, compared to when I'm closing the staple, which could have to do with the way I open and close the staples. So there is uncertainties also in how we perform experiments. In addition, there is also an uncertainty related to the counting, particularly as I at some stage became a bit distracted as I started to bleed from doing this experiment. So, then I transferred these data into Excel, so I could do some statistical analysis of these data, and first I made some calculation of the mean value, and the standard deviation. As you maybe remember from your days in studying statistics, what we now have done is to take a sample of staples, and based on this sample, we want to use so-called inference statistics to say something about at what number of cycles staples are expected to fail. Particularly, we want to estimate a safe number of cycles. So based on this small sample, we want to say something about all the staples in the world. You could say that this little experiment is rather irrelevant, and has nothing to do with real structures, but actually, laboratory experiments to predict at what load a beam or a column would break will give us similar statistical data, if the experiment is repeated a reasonable number of times. You may think from your physics lectures and material science lectures, that if a beam is made of a material that breaks at 500 megapascals, it will always break at 500 megapascals, but that is not correct. It will break at different levels of stresses, most likely around or above 500 megapascals, and we have to bring in statistics to get a grip of how to use these data to design safe structures. If you really depended on it, how many cycles would you say was okay, if you needed to be sure that a staple did not break? The lowest registered number is 8. Would less cycle than 8 be okay? Or would you be okay with more? Let's add a normal distribution curve to this data, based on the mean value and standard deviation that was calculated. The first thing we have to ask is, does the distribution function fit the data? Well, not too bad, but not perfect. The next thing we should ask is, if we say that we require less than 8 cycles, what is the probability that the staple will fail based on this distribution function? Our focus in a problem like this need to be on the lower end of the distribution, the lowest values, so we have to focus in on this part. One way of looking closer at the tails of a distribution, and to what extent it fit the chosen distribution function, is to draw the cumulative probability function, and plot the data in a cumulative form. The cumulative probability plot of the data is created by dividing the number of occurrences of cycles, from 0 to 28, which was the maximum number of occurrences registered, and dividing this by the total number of tests performed, plus 1. This n divided by n total plus 1 is called a plotting position. Other plotting positions do exist, but here we will use the most commonly used plotting position. As we can see, the cumulative probability distribution of the data, in blue, fits reasonably well the normal distribution function, in pink. If we plot the same data in a logarithmic y-axis, we get to see the fit in the lower end of the curve even better. Although some deviations can be seen, the normal distribution function still seems to fit the data rather well. We can also see that if we chose 7 cycles as the maximum, there is a 1% probability that the staple would fail. I will leave it up to you to ponder over if you think a 1% probability is good enough if you really depended on it. An even better way of checking if the data fits the distribution, is to draw the data in a probability plot, in this case a normal probability plot. In a probability plot, the data should form a straight line if they fit the chosen probability function perfectly. To create a normal distribution probability plot, we have to introduce a new variable, z, which is the inverse of the cumulative normal distribution of the pi calculated on the last slide. Here we can easily see that the data does not form a straight line in a normal probability plot, and as a result cannot be seen as perfectly normal distributed. Many alternative probability distribution functions do exist, and hopefully you have heard of the log normal distribution, and maybe the Gumbel distribution and the Weibel distribution, all of which we will use extensively in this course. Here, I have drawn a log normal distribution on top of the data. Here is the data in a log normal probability plot. The data does still not fully form a straight line, but it is better than when it was drawn in the normal distribution probability plot. The data can also be drawn in a Gumbel or Weibel probability paper, which indicates that Gumbel may be a good alternative to the log normal distribution, but Weibel does not seem to fit the data very well. However, let's say that we found the log normal distribution to be satisfactory. For 7 cycles, this indicates that there is a 1.6% chance of a failure. For 6 cycles, there is a 0.15% chance of a failure. The next question is naturally, what is an acceptable probability in a case like this? We have to get back to that question, but now, what we have seen in this lecture is there are uncertainties in the values we need to use in our calculations as structural engineers. We have shown that we can do an experiment or measurement, and collect the data from these to better understand these uncertainties. However, there are also uncertainties related to the experiments themselves, which are more difficult to include in further analysis so far. We can do statistical analysis of these data, first to find the correct probability distribution function, and then to estimate a safe value of the strength with the required exceedance probability.